Ladies and gentlemen, welcome to the Ryan the Ride Mechanic channel. I am Ryan the Ride Mechanic. Listen, I'm excited today because I'm going to be starting a multi-video thing series, I guess whatever you want to call it, where I'm going to go into launch rides, mainly electric powered launch rides like LSM and LIM, that sort of stuff. And I want to show you guys basically how they function and how they work, and I'm really excited to be doing it. So there's going to be a couple videos to this, so stick with it, and I want to get into it, but first we need to put on the brakes, quite literally. In this episode, I actually want to start out talking about eddy current brakes. So let's get right to it.
Now get ready. Here we go.
First of all, thank you so much for watching another one of my videos, and I'm glad you're here. Over these next couple of videos, I'm going to be sharing my knowledge and insight on things that I know pretty much. And I got this knowledge from working on these machines. So I didn't go out and do a lot of research and things like that to them. I pretty much picked this knowledge up by working on the machines. And I got the knowledge from the equipment's manufacturer and the people that have doctorate's degrees in mechanical and electrical engineering that design the things. So that's where my knowledge is coming from. If I reference a date or something, tag a history information, I'm not quite right about it, I apologize in advance, but it's just one of the little things I'm trying to add in to make the videos a little more useful to people. Oh, as a side note, I normally don't script these things, but this particular series, it's going to be, I don't quite know yet, it's going to be 3 or 4 videos long. Has so many bullet points and they all interact with each other so much, I had to write stuff down just to organize my thoughts so everything comes out in a seemingly useful fashion to everybody that you could understand and follow. The videos build off of each other, so this would be video number 1, whatever I'm going to call it, I don't know. So I just want to let you know, when you see all the cuts and jumps in my videos, it's because I'm reading my bullet points and trying to remember what I was going to say during that bullet point. So there'll be a lot of cuts in this video. Oh, that was one of my bullet points, in fact, was to get a teleprompter for the future. So over the last bunch of years, we've started to see magnetic brakes work their way into all the rides. And they are that way for a reason. Mainly the biggest advantage of magnetic brakes is that there's no contact, so there's no clacking of brake fins, there's no worn down brass that has to be repetitively replaced, and typically there's no wear on the vehicles either. So you've severely reduced the amount of maintenance to the vehicle and track and structure, and then you've also made the ride a little bit more reliable since the magnetic brakes are much smoother and they can deaccelerate the train quicker, smoother, faster than standard pinch style brakes can do. So we're starting to see them pop up on pretty much everything. There are 2 main styles of magnetic brakes. There are the type of brakes that are mounted where the magnets are mounted on the train, and the fins, the brake fins, are mounted onto the track. This is very common in standard roller coasters where magnets are underneath the train and fins are on the track. The other style is that have to do with like LIM style rides that use launch, like a synchronous or inductive launch. And those magnets are typically mounted on the track because the train already has the fins on them. The fins on the train are called reactive fins. So those fins are typically mounted on the train, always mounted on the train, I guess. And so there you see the brakes in the track. Typically, they do something like, there's 2 methods to applying magnetic brakes. The first one, actually, well, I guess there's 3, because you can leave one brake there as a trim, just where the train constantly runs over and it slows down the brake a bit, slows down the train a bit. The second one is to raise and lower out of the track, and this can be done both ways. You can raise and lower the magnetic what are they called? Shoes. You can raise and lower the magnetic shoe into the track, and you can also do the same thing with a fin depending on which ride you're on. So you see that a lot. Let's see, the shoes that lift and lower the track, you'll see them on, I know, the old Wicked Twister out at Cedar Point, which has been removed, and Volcano Blaster also was one of them. and the Flash ride. I guess it's now called Flash out at Discovery Kingdom, and there's a handful of other rides out there, but these are the ones I can think of off the top of my head. Those shoes will raise and lower into and out of the track. And then the rest of them you're much more familiar with seeing is like on a hydraulic launch ride. Those fins will lift up out of the track and lower back down the track. And then there's another one where the magnet stays in place all the time, but it slides apart. And by that I mean you have your north and your south magnet here, and they're aligned with each other to produce the maximum force. And then as the train comes through, the two literally slide this way apart from each other to break the field and allow that fin to pass through. That's a really common one on a lot of RMCs. You'll see that out there. Those two brakes will slide. It's not much. It's only about 1.5 inches forward to break the magnetic field to allow the train to ride through. So the next thing I wanted to talk about is why magnetic brakes are used. And at the beginning of the video I mentioned that because they're relatively no maintenance to them, and there isn't. I mean, there's really nothing to do to them. If they slide apart or move up and down, you're greasing a mechanism to keep them operating up and down smoothly. But the nice part about that is that whatever brake is in the applied position, whether it was fins up or shoes down or whatever it might be, that can be done with springs. So in the event of a power failure, air loss, system loss, anything like that, those brakes will come up, lower down, whatever they might need to do to slow down and stop the train. So that is one of the fail-safes that's built into the ride. So that's a good thing. Now, the other thing that magnetic brakes can't do is they can't hold a train. By that I mean they work off of eddy currents, and when you slow down the vehicle, the production of that eddy current goes away, and it can't hold the train in one position. So typically, on a track with multiple trains, you can use eddy current or magnetic brakes to slow the train down, but you cannot use it to stop the train. You say, well, the train can come to a stop. It's like, yes, it can, but if it were on a slight incline, it can still roll forward. If it was a strong windy day, it could literally blow the train forward into the next block. So typically, wherever you are, you still have multi-train rides. That is, you still have a mechanical pinch brake that activates as the block. So you'll have all those magnetic brakes and slow the train down, and then you'll have a mechanical pinch brake to hold the train once it's pretty much come to a stop. So at this point in the video, I wanted to say the standard, hey, if you like the video, please like and subscribe. It lets me know that you like the video, and subscribing to the channel helps me out and gets my views out there for more people. My audience is only a fraction of what it could be, not because I want more people, but because I know there's way more people out there that have these questions and they just haven't stumbled onto the channel yet. The typical response I get is, man, once I found your channel, I binge watched everything. It's like, I appreciate that. And as always, leave comments down below. People leave the greatest stories and stuff like that in there. So it's like, I love to see the comments. I love to read your stories. I'll answer questions if I can answer them. It's just one of the things I love to do. So please make sure you like and subscribe. And share the video if you want to. If somebody else likes the stuff too and they don't know anything about it, just hit that share button and send it on over to them. That way they know about it too. All right, so let's talk a little bit about construction. So what are magnetic brakes made out of? There are two main components to a magnetic brake. There is the brake, the magnet itself, which is a neodymium magnet. Hard to see, I know, they're small. This is a neodymium magnet. This is also called a rare earth magnet. This one's only about 1 inch tall, 1/2 inch wide, and about 3/16 of an inch thick. Anyways, these are permanent earth magnets. They are the strongest magnets pretty much on Earth. So they have the most attraction. And when you use them the opposite way, they're the strongest to repel as well. So a brake is lined with these guys, but they're about 3 inches tall, 2.5 inches wide, and about an inch thick. So they're extremely powerful. One of the things you get when you buy magnetic brakes is a booklet of warnings that come with it. All the stuff like, hey, if you're holding a wrench and you get your wrench near that magnetic brake, and people instantly go, oh yeah, the wrench will get stuck to the brake. It's like, not quite. Actually, the wrench will find the air gap between the brake, right? The gap that the brake fin goes through, that's the strongest area, and it will pull that wrench into that gap with your fingers still around it. And it can literally cut your fingers off. It's so powerful. So there's all sorts of warnings about, hey, don't do this, don't do that. When we were working on magnetic brakes, I actually told the crew to go to the wood shop and get a piece of wood, about, I think, 3/4 inch plywood, 1/2 inch plywood, something like that. Normally was close. And you cut a strip of it off about 7 inches tall and about 1.5 feet, 2 feet long, depending on what you're working on. And what they did is they slid that down inside the magnetic gap first. And then they just used, since we were working on it, we just used some duct tape to hold it there. But that was the last ditch effort in prevention to make sure nothing went down inside that gap. We basically filled the gap so nothing can go in there. So magnets are extremely powerful. And then the way those work is inside the magnet, inside the shoe, there is a north facing magnet and a south facing magnet. And the two are lined up with each other. So there is the maximum amount of pulling between the two. And then when you look at that from the top, you'll find that there's more magnets in there, of course, lining the entire length of it. And they oscillate polarity. So you have a north, and then a south, then a north, then a south, then a north, then a south, all the way through. And on the opposite side, the same magnets are also inverted to match their polarity as well. So you have a north here and a south here, and then a north here and then a south here. So they're constantly flip-flopping all the way down through there. So they're extremely powerful. You don't want to get anything around them. Now, on the train, if it's a limb ride, or on the track, if it's a standard roller coaster, you have the fins that go through them. The fin on a ride, like a linear induction ride, is called a reaction fin. When they're mounted in the track, they're simply reactive fins, or just referred to as brake fins, braking fins. No real fancy names to them. And the big question is, what are they? What are they made out of? Are they just steel? It's like, no, they're not. Steel is magnetic, and to create eddies, you do not want a magnetic material. You want a ferromagnetic material, or if I'm using that right, I'm pretty sure I am. You want something that's not magnetic. So actually what they are is a mixture of mainly aluminum and copper and nickel. I believe there's a plating or something in them that's nickel. Nickel is very small in them, but the main three components are basically copper, aluminum, nickel. And those create the greatest reactive force. And by that, I mean they create the largest eddy. Now, an eddy current is what the brake actually operates off of. So eddy currents are very interesting little things. Basically, you take a very strong magnet, like a neodymium magnet, and you put a plate of aluminum in front of it, and then move the magnet back and forth, and it starts feeling like the magnet is in syrup. It actually has a resistance to it. And you say, well, it sticks really good to steel. It's like, yes, it does stick really good to steel, but if you put that magnet on a car, like a little Hot Wheels car, and roll it across a steel plate, that car goes just as fast over the steel. The magnet actually doesn't slow down. But if you run the same experiment with aluminum, it slows right down and comes to a stop in aluminum. Fun little trick. So the eddy current is basically a residual current that's left in the aluminum fin. We're just going to say aluminum or reactive fin, whatever. It's a residual current that's left inside of there. So as the magnet moves, let's just call the polarity of the magnet positive, although there's opposites of each side, so it's kind of not quite fair to say, but for simplicity, let's just say it's positive. As that you put that magnet on that aluminum plate and then you move it, well, what was left from where that magnet was is actually a negative eddy current. And again, these are simplified ideas. The actual eddy currents and how they function, I've seen term papers and books and stuff written on it. It's an extremely complex subject, but I'm trying to fit it into a video. So we're gonna go down to terms that I can understand and most people can understand. So basically, take a positive magnet, put it on a plate of aluminum, and then move it, and there's a negative force left there. Opposites attract, basically, right? So as you move it, that negative tries to stay with the positive, but it can't. The slower you move it, the worse off it is. The faster you move it, the stronger it becomes. Pretty interesting, right? All right, so in the theory of standard halfway demonstrations that I'm kind of good at, we're going to use a reactive fin. See that? There we go. Reactive fin. We're going to take that guy, and then we're going to take a positive magnet. High-tech illustration right here. And we're going to take this magnet and put it on here like this. Now, as we do this, this magnetic force, if you move it, doesn't do anything to this reactive fin. It just sits there. But if you take this force and you move it quickly to one side, and just fast as you can, just go pull it, it leaves a negative eddy onto that fin. That eddy almost disappears as fast as it goes. So they don't last long. This is the reason why you can't stop a train using only eddy current brakes. Because as soon as that train actually comes to a stop, the eddy goes away as well. And you're just left with your reaction fin. Now, if you move slow enough, you can roll just right out of whatever brake you're sitting in. So that's the reason mechanical brakes are used at the same time. But that is a super simplified version of it. Basically, you take your magnet, do it again. You take your reactive fin, right? Put your positive magnetic force on it, and really not much happens if you move it slow, right? But if you do it fast, there's your negative right underneath it, okay? When I would give tours at the park, which I didn't have to all the time, but I did it occasionally. When I gave tours at the park, I would take them to our impulse coaster, which we had a platform out underneath the brakes that you can go walk out to, where you can get within about arm's reach of that brake. And what I did is I took the operator's, and this is while the park was closed. So I took the operator's height stick. The height stick was actually an aluminum measuring stick. I took that height stick and went over and demonstrated to people that through the limb, that stick could move freely because there was no magnetic force. But through those brakes, I pushed it through there, and you could see where every single one of those magnets was, because every time it hit a magnet, it's almost stopped. Pushed really hard against it, and it was like, and then finally came out of that magnet. And then I would ask people if they wanted to try. And pretty much almost everyone wanted to try. Some people didn't, which was fine. But they basically got their best samurai sword swing and tried putting that height stick through that brake. No one could do it because it was just that forceful and stopped that much. The last part of the equation is the actual fin itself. The longer the fin is, the less reactive it is, because the eddy currents are kind of able to swirl out and they just kind of dissipate in the big fin. But as the eddy current gets close to an edge, it has nowhere to go. So the braking force intensifies as it comes up to the edge of a fin. So if you notice on limb coasters, it's very hard to find these pictures of like a launch ride with out of the stators, but I have some. I was able to find some. So the middle fin on a limb coaster is typically solid. It's a solid piece all the way down. But the outer fins are actually split in the center. And the reason they're split in the center is because they wanted that much braking force into the train. So those outer ones are the ones that the train actually slows down on. So those are the ones that actually do the stopping. So they wanted a higher stopping force, so they split the fin. So it was harder going through all those brakes. And the train came to a stop faster. Some of the force of the stopping can also be adjusted by the air gap. That's between the two sets of magnets there. If you widen the air gap, it stops less. If you narrow the air gap, it stops more. It's a very finite adjustment with that stuff, and not much can be done to it. That's mainly a function of how much the train drifts. Like you say, well, like the fin's only 6 millimeters wide. It's like, well, okay, so you could put a 6 millimeter air gap in there. It's like, no, the train drifts left to right about 6 millimeters in each direction. So that's 6 plus 6 plus 6. So you need an 18 millimeter gap, bare minimum. Otherwise, the train's fins would strike that. And you know what? Those fins are not cheap at all. And despite them being made out of aluminum and copper, they are not lightweight at all. It typically takes 2 people to lift those things. And then the last component of the brake, which is very, very minor, but it is the backing, which is actually a heavy iron backing. And the iron helps. It's kind of odd. The iron helps reflect the magnetic field backwards into there, which is kind of opposite what it does on induction motors. I'm not sure how it works there. It's the opposite of an induction motor. It helps pull the force away from it to straighten the field out. But again, not a scientist. It's way above my pay grade. All right, I'm Ryan the Ride Mechanic. I hope you've enjoyed this little segment on eddy current brakes, and I will see you in the next video. Take care. Bye-bye.